Traditional naval architecture dictates that you store your most volatile assets, specifically dozens of tons of highly explosive missile warheads, deep within the armored core of the ship, insulated by layers of bulkheads, fuel bunkers, and crew compartments to protect them from incoming kinetic penetrators. The $22 billion Zumwalt-class destroyer violently rejects this century-old conventional wisdom. Let us execute a longitudinal Boolean cross-section cut along this 182-meter, 15,000-ton stealth behemoth. I am stripping away the specialized radar-absorbent composite skin, peeling back the carbon fiber stealth geometry to reveal a highly unorthodox mechanical reality underneath. Look closely at the extreme perimeter of the hull. Instead of a densely packed, centralized missile magazine hidden deep in the bowels of the vessel, the Zumwalt distributes exactly 80 Mark 57 peripheral vertical launch system cells, or PVLS, directly along the outermost edges of the ship's architecture. The aerospace and naval engineers have literally taken the most explosive components of the vessel and weaponized their placement, turning them into a massive, reactive armor belt, wrapping around the crew like a volatile exoskeleton. To fully grasp the sheer thermodynamic and mechanical insanity of this structural design, let us isolate and extract a single Mark 57 module from the massive 3D matrix. Zooming in on the concentric canister launcher, you can see it is not just a dumb steel tube holding a rocket. It is a highly sophisticated, self-contained thermodynamic management system built to withstand extreme dynamic stress. At the very base of this vertical structure lies the exhaust plenum, a heavily reinforced, multi-layered chamber designed to capture and seamlessly redirect the catastrophic kinetic energy of a missile launch. When a solid rocket booster ignites within this confined geometric space, it instantly generates a localized exhaust temperature exceeding 3,000 degrees Fahrenheit, which is roughly 1,650 degrees Celsius. To put that thermal load into a real-world perspective, that is an environmental temperature entirely capable of melting pure industrial iron into a liquid puddle within seconds. To prevent the composite canister and the surrounding ship structure from instantly slagging into molten metal, we must activate the high-pressure deluge system. The exact millisecond the launch sequencer sends the electrical firing impulse to the missile, massive industrial-grade hydraulic pumps slam open emergency blast valves, injecting a staggering volume of high-pressure cooling water directly into the supersonic exhaust plume. This creates a violent, explosive phase change, instantaneously turning the liquid water into ultra-high-pressure steam. This steam expansion physically forces the toxic, superheated exhaust gases to route up and out through the heavily armored uptake flues, safely venting away from the delicate phased array sensor grids mounted on the superstructure. But what happens if the launch mechanism fails catastrophically? Let us run a maximum yield catastrophic failure simulation. I am initiating a sequence where a BGM-109 Tomahawk land attack cruise missile, fully loaded with a 1,000-pound conventional high explosive warhead and a completely full Stage 1 solid rocket motor, experiences a catastrophic mid-canister detonation. In a traditional centralized Mark 41 VLS found on older destroyers, this localized explosion would propagate inward, tearing through critical structural bulkheads, instantly igniting the adjacent missile cells in a sympathetic detonation chain reaction, and effectively breaking the ship in half from the inside out, similar to snapping a steel spine over your knee. The Mark 57 PVLS prevents this total vessel loss through a structural concept known as a frangible outward architecture. As the simulated detonation violently expands, it generates a localized overpressure wave exceeding an unimaginable 1 million pounds per square inch. Observe the inner bulkhead, the thick, unyielding wall separating the detonating missile cell from the internal crew compartments and the high-voltage power grid. This specific barrier is forged from ultra-high tensile naval steel, deeply fortified with layered Kevlar spall liners, acting as an unyielding kinetic shield against the blast. As the supersonic shockwave slams into this dense inner wall, the mechanical kinetic energy is violently reflected outward. Now, shift your focus to the outer hull plating, covering the missile cell facing the ocean. This is the blowout panel. Unlike the rigid inner bulkhead, this outer carbon composite skin is mechanically engineered to fail under stress. It is pre-scored at the molecular level and fastened with specifically calibrated shear bolts designed to cleanly fracture at a precise pressure threshold. The exact moment the 1 million psi shockwave bounces off the inner armor, it hits this weakened outer panel, violently shattering it into 1,000 pieces. The catastrophic overpressure, along with the 2,000-degree plasma fireball and jagged shrapnel, is instantly vented horizontally out into the open ocean. By purposefully sacrificing the outer edge of the ship, the design safely dissipates the overwhelming kinetic energy into the atmosphere rather than allowing it to crush the internal compartments and the crew inside. It is a brilliant, brutal display of sacrificial engineering. However, physically distributing hundreds of thousands of pounds of heavy ordnance along the outermost margins of the ship introduces extreme physical penalties, particularly when integrated with the Zumwalt's highly controversial, radical Tumblehome hull. Unlike a traditional flared hull that widens as it meets the main deck, providing increasing reserve buoyancy and pushing back against the water when the ship rolls, the Zumwalt's Tumblehome hull narrows as it goes up, angling inward at a sharp, aggressive 50-degree slope. Let us activate the hydrodynamic physics engine and drop this top-heavy 15,000-ton steel structure into a simulated Sea State 6 environment, featuring unpredictable, towering 10-meter rogue waves. Notice how the deliberate placement of the 80 fully loaded Mark 57 cells pushes a massive concentration of dead weight to the extreme lateral edges of the ship. This wide peripheral mass distribution severely alters the vessel's metacentric height, the most critical engineering metric in naval architecture that determines a floating object's inherent tendency to self-right after experiencing a severe roll. As the massive, tons-heavy wall of water strikes the side of the inward-sloping Tumblehome hull, the lack of an outward flare means the ship does not naturally resist the roll with an increasing volume of buoyant displacement. Instead, the sharp hull cleanly slices through the wave, and the immense, concentrated weight of the peripheral launch cells acts exactly like a heavy rotational pendulum, rapidly accelerating the rolling momentum. If the ship takes heavy battle damage on one side, and a section of these peripheral launch cells is flooded with seawater, the sudden asymmetrical weight distribution would immediately drag the damaged side deeper into the ocean. The hydrostatic pressure acting on the inward-sloping hull would aggressively compound the list, potentially overwhelming the automated hydraulic ballast transfer systems and pushing the vessel past its critical angle of vanishing stability, resulting in an unrecoverable, catastrophic mechanical capsize. The aggressive stealth geometry, combined with the heavy explosive armor concept, creates a razor-thin, highly dangerous margin of error in open ocean fluid dynamics. This is the sheer, unforgiving physical cost of trying to rewrite the fundamental laws of naval architecture from the ground up, let us transition from the chaotic hydrostatic simulation directly into a high-intensity live-fire combat sequence to analyze the sheer mechanical stress of weapon deployment. I am tracking a digital firing command as it surges at the speed of light through the heavily shielded fiber optic neural network of the bridge down into the engineering hull. Let us render the outer composite armor completely transparent to observe the monstrous integrated power system in action. Deep within the engineering spaces, two massive Rolls-Royce MT-30 marine gas turbine engines, essentially the exact same aerospace power plants used to thrust the massive Boeing 777 commercial airliner through the sky, are violently screaming at a maximum operational rotation. These twin turbines do not connect to a traditional mechanical drive shaft or physical propellers. Instead, they operate as a colossal 78-megawatt floating power plant. They instantly generate a massive 4.16 kilovolt alternating electrical current, surging this extreme high-voltage plasma directly into the combat systems grid to ignite the solid rocket booster of a RIM-66 Standard Missile 2. As the 1.5-ton interceptor violently tears its way out of the Mark 57 peripheral cell, we can visually track the extreme kinetic recoil propagation. The physical launch generates a staggering downward thrust vector, transferring thousands of pounds of instantaneous mechanical force directly into the titanium-reinforced skeletal frame of the hull. You can literally see the microscopic stress fractures in our structural simulation as the missile rips through the atmosphere at Mach 3, which is roughly 2,300 miles per hour, generating enough atmospheric kinetic friction to melt standard aluminum into glowing slag. Now, let us place this peripheral launch architecture directly onto the tactical combat scale against its primary contemporary rival, the Flight 3 Arleigh Burke-class guided missile destroyer. I am pulling up a highly detailed side-by-side three-dimensional schematic comparison. The Arleigh Burke utilizes the traditional Mark 41 vertical launch system, packing a densely concentrated cluster of 96 missile cells right into the dead center of the ship's structural core. This centralized design offers maximum offensive payload density in a compact physical footprint, but it introduces a catastrophic thermal and kinetic vulnerability. If a supersonic Chinese YJ-12 anti-ship cruise missile manages to bypass the Aegis combat radar system, pierces the outer steel hull, and penetrates that central Mark 41 magazine, the resulting sympathetic detonation of 96 loaded missile warheads will instantly vaporize the entire ship from the inside out, creating a massive blast radius comparable to a small tactical nuclear warhead. The Zumwalt purposefully sacrifices total offensive firepower, carrying only 80 peripheral launch cells to secure absolute mechanical and physical survivability. If an enemy kinetic warhead strikes the Zumwalt's flank, the localized explosion will violently blow out a specific section of the peripheral armor, venting the multi-thousand-degree kinetic plasma harmlessly into the ocean, while the unyielding internal titanium bulkheads preserve the central engineering core and the primary human crew compartments. The Zumwalt was structurally engineered to take a direct supersonic kinetic punch to the jaw and stay afloat. However, here's the fatal mechanical flaw that effectively killed this entire $22 billion stealth program. The peripheral VLS architecture is an absolute engineering masterpiece of thermodynamic control, but the entire ship was designed around a central weapon system that completely failed the unyielding laws of economic physics. Let us shift our 3D camera forward to the massive sloping bow of the ship to examine the Advanced Gun System, or AGS. These two massive 155mm automated deck guns dominate the entire forward geometric profile of the vessel. Let us cut away the carbon fiber stealth housing to expose the cavernous, multi-deck automated ammunition handling system, plunging deep into the lower hull. This complex robotic magazine was physically engineered to hydraulically feed long-range land attack projectiles at a sustained, punishing rate of 10 rounds per minute. The mechanical tolerances of these robotic loading arms are flawless, yet the system is completely dead. The specialized LRLAP ammunition required to fire this weapon was highly customized, featuring complex deployable GPS guidance fins and a miniaturized rocket motor to strike targets nearly 80 miles away. Because the Department of Defense drastically cut the Zumwalt production order from 32 ships down to a mere 3 hulls, the fundamental economy of scale violently collapsed. The unit cost for a single 155mm artillery shell exponentially skyrocketed to a staggering $800,000. Firing a single sustained barrage from these mechanical guns became financially equivalent to launching a multi-million-dollar Tomahawk cruise missile, but delivering only a tiny fraction of the explosive payload. Consequently, the United States Navy officially canceled the ammunition procurement program, leaving this magnificent stealth destroyer with 2 massively heavy, completely useless mechanical paperweights permanently bolted to its forward deck. Thousands of tons of hydrostatic displacement, incredibly complex liquid cooling lines, and highly fortified deck space were utterly wasted on a heavy weapon system that cannot fire a single shot in anger. By sacrificing so much central deck space and internal volume for the useless AGS, the Zumwalt was physically forced to limit its missile capacity to only 80 peripheral cells. Thus, this $22 billion technological marvel, possessing the most advanced radar-absorbent Tumblehome hull and the most survivable explosive armor system ever deployed on the water, ended up as a bloated, overpriced missile carrier, packing less actual vertical firepower than the 30-year-old, significantly cheaper Arleigh Burke destroyers it was explicitly meant to replace. The structural engineering was brilliant, but the strategic execution was a catastrophic failure of mathematical and logistical proportions. The Mark 57 peripheral vertical launch system remains one of the most innovative thermodynamic and kinetic energy management designs in the history of modern naval warfare, proving that you can literally weaponize the very missiles meant for destruction into a reactive armor belt. But a perfect localized armor system cannot save a warship built around a physically hollow and economically broken core. If you were the Navy admiral sitting in the Pentagon, would you bet $22 billion of taxpayer money on a ship that cleverly protects its crew by blowing itself up, only to realize you literally cannot afford to buy the bullets for its primary guns? Let us know in the comments below. Do not forget to subscribe to DEFUNCT and hit the notification bell right now so you never miss our deep dive mechanical teardowns into the world's most fascinating engineering failures.